Hi there, it's Miss Heaton signing in to talk to you about solutions. In this unit, we are going to be talking about a lot of different things. So this screencast is going to introduce you to some of the basic key terms and ideas that we're going to be building on throughout the unit. So today, our biggest goals are this. First, we need to figure out how to classify mixtures. We're going to add on to what we already know. Secondly, we're going to talk about what happens when you form that mixture. What is happening to those molecules? And thirdly, why are there some things that do dissolve to make mixtures, and why do other things not? So first thing I want you to do is think back to what you already know. You can make a Venn diagram that has homogeneous mixtures on one side and heterogeneous on the other. Think back to what you know about those words. What does each type of solution look like? What forms it? Maybe put some examples in there. So hit pause and try that. So both mixtures are made of more than one substance. So it's not just pure water, it's water with something in it, for example, or milk mixed with something else. Homogeneous means it's the same throughout. Heterogeneous means it's different throughout. Now, this works for most cases, but there are some mixtures that are in between, not clearly homogeneous, not clearly heterogeneous. You may remember this from Unit 2. It was hard to classify some things. So now that we know a little bit more about chemistry, we're going to redefine these categories and actually use 3 different words to talk about mixtures. And that's what you see on this table. At the top here are the 3 kinds of words that we're going to use. We're going to talk about solutions, colloids, and suspensions. So let's go through some basic info about each of these. Solutions are similar to homogeneous mixtures. They are the same throughout. It doesn't even look like it's a mixture. Colloids are in between, and then suspensions are more heterogeneous. Let me give you some examples. Solutions are things like salt water, so salt dissolved in water, or soda that has carbon dioxide and other things dissolved in water. A colloid would be something like milk or clouds or shaving cream, where it's kind of cloudy and you can see some of the pieces, but not all. And then a suspension is something like trying to mix flour and water, or sand and water, or like Italian salad dressing that separates when you let it sit for too long. Now, if you don't know what's in something, you can do a few tests to figure out what kind of mixture it is. First of all, you could filter it, like put it on a funnel, put a piece of filter paper in there, and try to pour the solution through, or the colloid through, or the suspension through. What you would see is this. In a solution, you would not be able to separate it in its 2 parts just by filtering it. Like salt water, the salt and the water are going to go through the filter paper. Same thing for colloids. The milk would go through the filter paper. But a suspension can be separated this way. If you took sand and water or flour and water and tried to do this, you would end up with the flour or the sand on the filter paper and the water going through. Another property is how they scatter light. Solutions do not scatter light. And what I mean by that is kind of look cloudy or make light go in different directions. Solutions don't. They look like they're transparent. You can see straight through them. Colloids, on the other hand, look kind of cloudy. And we call this the Tyndall effect. You may see a demo in class related to this, but these are going to scatter light in all different directions. If you try to shine a laser through it, you'll be able to see that laser beam. And then suspensions also exhibit the Tyndall effect. And the reason for these properties is this. Solutions have the smallest particles. Whatever you're trying to dissolve has broken up into tiny pieces. Colloids have medium-sized pieces, and suspensions have the largest pieces. So we could kind of classify our mixtures based on this. Like, let's say you have an unknown mixture, and you're trying to figure out what it is. First step, you may want to filter it. If it can be filtered, automatically you know that it is a suspension. If it can't, you either have a solution or a colloid, so then you maybe move on to look at its appearance. When you try to shine a light through it, is it transparent or does it scatter light? Is it kind of cloudy? If it's transparent, it would be a solution. If it's cloudy, it's a colloid. Well, in this unit, we're primarily going to focus on solutions. These are the most important to chemists. And inside this solution, or this homogeneous mixture, you've got 2 parts. You've got the solute. This is the thing that's being dissolved. And typically it makes up less than half of your mixture. So it's the minor portion. The major portion of your mixture is the solvent, the substance that does the dissolving. Typically this is water, and it makes up usually more than half of your mixture. Don't confuse these 2 words, actually all 3 of these words. They start with S's, they mean very different things, even though they're kind of similar. Here's what's happening when you make a solution. What we have here is a picture of salt. So we've got sodium and chlorine. Sodium's the gray, chlorine's the blue. And then water. Water, oxygen is the red, and the gray ones are hydrogens. What you see is that the sodium chloride is dissolved when several waters gang up on one of the chlorines and pull it away. So that's what they're doing here. They're ganging up on one chlorine and pulling it away. Or they gang up on one sodium and pull it away. So a solution is formed when bit by bit the solvent breaks up the solute. This is different than reacting. The water is not reacting with the sodium or the chlorine, it is simply separating the sodium and chlorine atoms from each other. This is a physical change because you can undo it. If you make salt water, you can regain your salt by evaporating away the water. Now, there are some things that don't make solutions. They would maybe make a suspension. An example of this is oil and water. If you try to mix oil and water, you may be able to mix it temporarily and see those little bubbles of oil and water forming. But eventually, if you let it sit, the oil is going to separate back out to the top, and the water will be on bottom. The reason that they don't stay mixed is because they have different polarities. Remember this from last semester? Oil is non-polar, meaning that there's no pull in one direction and another. So we call it hydrophobic. You may remember that from biology. It's afraid of water, so it won't mix with water. Water is the opposite. Water is polar, and it's hydrophilic. It loves finding other waters. So the waters are all going to form these little intermolecular forces, these hydrogen bonds with each other. And the oil is not going to be able to get through those connections or form those connections with the water. And so they don't form a solution. I didn't show you the animation, but the whole idea is that only some things form solutions. But there is kind of like a scale from totally insoluble, totally not able to dissolve, to completely soluble. Soluble means that the solute will dissolve to some degree or another in that solvent. So salt is soluble in water because it will dissolve. Oil is insoluble. The solute of oil won't dissolve in the solvent of water. But maybe oil is soluble in something that is also nonpolar, like hexanes. Everything that's soluble does have some sort of limit to how much can dissolve. So there aren't things that are like infinitely soluble. And what we're going to be looking at over the next couple of days is how do we classify the solubility? How do we quantify it? At what amount of solute and solvent and what amount of temperature will they be soluble? And so if you have a solution, you can talk about it being saturated all the way to supersaturated. And this describes the degree to which the solute has been dissolved in the solvent. An unsaturated solution is where it's possible that you could add more solute. So you're not at your limit yet. Maybe this is how your brain feels walking into a class. By the end of class, you may feel like your brain is saturated. You can hold no more knowledge. A saturated solution has the maximum amount of solute in it that can dissolve. So if you try to add more, it's just going to sink to the bottom. It won't dissolve anymore. And then finally, this is a really unique category, a supersaturated solution. This is something that happens when you heat up to a higher temperature, more dissolves, and then you cool it back down to room temperature. So now it's exceeded what it should be able to hold at this temperature. This is actually a very unstable situation, and if you disturb it at all, crystals can form. You may get to see a demo or a lab of this in class. It's pretty cool. So let me repeat a couple key things here. Unsaturated solutions have less than the max of solute that they could have. And the way you can tell if it's unsaturated is if there's no solid, no solute, remaining in your flask. A saturated solution may also look like an unsaturated solution if it's right at its saturation point. If it's above that, like if you added more salt than the solution can hold, the salt will just sink to the bottom. So this saturated solution, the solute, the water is holding as much solute, the solvent, water, is holding as much solute, sodium chloride or whatever, as is possible at that temperature. And you may see undissolved solid in your flask. And then finally, supersaturated. Oh, here's a great picture. So this solution on the left is supersaturated, and if you just disturb it a little bit, you see these crystals start to form, and eventually the whole thing crystallizes as the solid that shouldn't be able to dissolve at room temperature starts to realize, oh, I should be a solid, I should not be dissolving, and it makes these beautiful crystals. The solvent here in a supersaturated solution holds more solute than it should be able to hold, And as I mentioned, these are unstable. And what they did to make these crystals form is they added a seed crystal. And we call that just like one tiny little crystal that disrupts the very tenuous situation going on in that supersaturated solution. Okay, folks, that is it. Bring your questions to class, and we will practice using these terms over the next few weeks.